We continue the lecture 9.7. We will work out the expression of new homomorphisms in coordinates by finding the associated matrix with certain bases first. We determine the expression in coordinates of the counterclockwise rotation in R2 about the origin. Geometrically, the function R alpha, this is the name we will use for the rotation counterclockwise by an angle alpha, takes a point P and rotates it by an angle alpha around the origin counterclockwise. The rotation axis is the origin. We take a ray starting from the origin and passing through P. We take another ray that forms an angle alpha with the first ray, and the image of P will be obtained taking a point on the second ray at the same distance to the origin as P. We will call this R alpha of P. In this case we are quite lucky, since a clever basis for finding an associated matrix of R alpha is precisely the canonical basis of R squared. The map, this rotation we are considering now is a homomorphism from R squared to R squared. The canonical basis is of R squared, hence it comprises these two vectors, 1, 0 and 0, 1. To see this, consider the following drawing. Why is this clever? It is clever because the rotation acts in an easy way on these two vectors, and the images are easily expressed by the same two vectors. So let's see this picture. The E1 vector is drawn here. If we rotate it by a degree of alpha counterclockwise, we will be getting this dot pictured on this ray, and similarly E2 is on the y-axis at distance 1 from the origin, and if we rotate by an angle alpha counterclockwise, we will be getting this point on this new ray, which is orthogonal to the previous one. What are the coordinates of the images of E1 and E2? This is just basic trigonometry. By basic trigonometry, the coordinates of the images are cos alpha sine of alpha for R alpha E1, by definition of cosine and sine. Actually, this coordinate is cos alpha, and this one is sine alpha. And in a sense, by symmetry, the coordinates of R alpha of E2 are, the x-coordinate is negative sine of alpha, and the y-coordinate is cosine of alpha. So we can write these images in function of the canonical basis of the codomain. So remember that we are considering canonical basis for the domain and the codomain. And any vector of coordinates cos alpha sine of alpha is expressed as a linear combination in function of a canonical basis by taking the coordinates as coefficients of the two vectors E1 and E2. And the same goes for the image of E2. We end up with these very easy expressions of the images of the canonical basis of the domain in function of the canonical basis of the codomain. I remind you that what we are trying to compute is this matrix, the associated matrix with respect of the canonical basis of domain and codomain, which amounts to finding the expression of R alpha in coordinates, as we have seen in the previous lectures. By definition of associated matrix of a homomorphism with respect of a basis of the domain and codomain, we have seen this in lecture 9.4, we have that the associated matrix of R alpha equals, as a first column we have the coefficients of the linear combination of the image of the first vector U1, cos alpha, sine of alpha, and the second column are the coefficients of the linear combination expressing the image of E2, that is negative sine of alpha, cosine of alpha. Since the matrix is with respect of the canonical basis, both of the domain and codomain, we derive the expression in coordinates of R alpha at once. See the motivation in lecture 9.6. R alpha, acting on a generic vector x1, x2 in the domain, equals the multiplication of x1, comma x2 written as a column vector on the left by the associated matrix, and then transpose again the column vector that we obtain. And the explicit expression is as follows. First coefficient of the image is cosine of alpha times x1 minus sine of alpha times x2. Second coefficient, sine of alpha times x1 plus cosine of alpha times x2. We make now a few remarks about rotations in R3. For general rotation axis, the associated matrix with respect of the canonical basis is quite complicated. On the other hand, if we restrict to one of the coordinate axes, x, y, or z, as a rotation axis, the situation is entirely similar to the rotation in R squared. Let's assume, for example, the y-axis is the rotation axis, and call Ry, alpha the map from R3 to R3, the associated rotation. Now, the first fact that we have is that Ry, alpha is an homomorphism. Well, in fact, any rotation in R3 is an homomorphism. Ry, alpha acts understandably on the canonical basis. It leaves the y-axis fixed and rotates by alpha counterclockwise the xz plane. Thus, the image of E2 equals E2. E2 is the vector that generates the y-axis. The image of E1 turns out to be cosine of alpha times E1 minus sine of alpha times E3. And this is computed exactly like in the with the same technique in the drawing that we have used just a few minutes ago. And the image of E3 is sine of alpha times E1 plus cosine of alpha times E3. The last two equalities follow from the first part of the lecture and the positive orientation of the Cartesian axis. What's the positive orientation of Cartesian axis? There are basically two orientations of in the three-dimensional Cartesian axis. One is with the z pointing up and x and y as drawn. This is called the positive orientation, and then the negative orientation is the one with the z axis up and the x and y axis that are switched. This shows that the associated matrix of Ry, alpha with respect to the canonical basis of domain and codomain is the following matrix. The first column, cos alpha 0 negative sine alpha, and this translates this equality. The second column is 0 1 0 and translates this equality. And the third column uses the coefficients of the linear combination of this equality, the image of E3, sine of alpha plus 0, E2 plus cosine of alpha times E3. Similarly, we have the associated matrix of Rx, alpha, which is counterclockwise rotation about the x-axis of an angle of alpha with respect of the canonical basis of domain and codomain looks like this matrix, and the rotation about the z-axis with respect always of the canonical basis domain and codomain is this matrix. And I have not written down explicitly, from these matrices we can immediately express the rotations about the coordinate axis in coordinates.